Hello everybody. I hope all of you are well and fine at your homes. Today I am here to discuss part of the chapter that we have got in your syllabus of engineering materials, the chapter of phase diagram. So till now we have studied the phase diagram of materials or alloy system, you may say, in which the two metals are soluble in both solid and liquid phases, and in that phase diagram we saw that the entire diagram is divided into three sections by two lines. One is called the solidus line and another is called the liquidus line. Clear? But now we will move forward to some more complex phase diagrams. Now first of all we'll study about the binary alloys which have solubility in liquid phases but has no solid solubility. That means what? In solid form they are not at all soluble in each other. One of the best examples is the alloy system of cadmium and bismuth. Here we can see that the liquidus line is not continuous anymore. In the previous phase diagram we saw that both the solidus and liquidus lines were continuous, but here the liquidus line is now not continuous. It intersects the solidus line at a point which is called the eutectic point. Now the eutectic temperature is 144 degrees centigrade for this diagram, and the eutectic composition is 40% of cadmium in bismuth. And the eutectic reaction that does take place is liquid, which on cooling or in the inverse direction on heating gives solid cadmium plus solid bismuth. Well, this phase diagram is a bit more complex than the previous one, in which both the metals were soluble in both solid and liquid phases, but here it has gone a bit complicated. Moving on to the next diagram, we'll see the phase diagram alloy system which has got full solubility in liquid phase but has got partial solubility in solid phase. One of the most good example of this type of binary alloy system is the alloy system of lead and tin, which is also known as soldering alloy because it was extensively used for soldering purpose. Now the diagram gets updated. Here the liquidus line is not continuous, just like the previous diagram, and the liquidus line has been shown as red, and the solidus line is also non-continuous over here, unlike the previous diagram, and it is in black. And we see two more lines which are called the solvus lines, which are shown in red over here. Now the liquidus and solidus intersect at this point, and it is called the eutectic point. The eutectic temperature is 183 degrees centigrade, and the eutectic composition is 62% of tin in lead. Now what does the solvus lines denote actually? Now before that we can see that alpha and beta phases are there. Now alpha phase is nothing but the solution of tin in lead, and beta phase is nothing but the solution of lead in tin. Now it can be seen that the maximum solubility of tin in lead is 18%, and that too at 183 degrees centigrade. But as the temperature decreases, the solubility of tin in lead decreases, and this decrease in solubility of tin in lead is shown by this solvus line. Similarly, the decrease in solubility of lead in tin has been given by solvus line 2. Now if we consider the reaction that is taking place at the eutectic temperature, eutectic point, then the reaction is given by liquid, which on cooling turns into alpha plus beta, when where I have said alpha is the solution of tin in lead and beta is the solution of lead in tin. Now, when we come into the application part of engineering materials, we see that iron has taken a prominent role in that case. Most of the metals that we use in our everyday life or in industries are generally iron and alloys of iron. So the phase diagram of iron and carbon is especially very important, which we are going to discuss in the next part. But before that, we must go through the allotropic forms of iron that it exhibits. Now, on increasing the temperature of iron, it can be seen that its crystal structure changes, which means that it gives different phases. For example, up to from room temperature to up to 910 degrees centigrade, we can see iron generally exhibit BCC structure, and this iron is generally magnetic in nature, and it's called the alpha iron or ferrite. On increasing the temperature further, say up to 1404 degrees centigrade, we get FCC structure of iron, and that iron is called gamma iron or austenite. On further increasing the temperature from 1404 degrees centigrade to 1539, which is the melting point of iron, we see delta iron, which is BCC in structure. Now, the heat treatments which are generally done in the iron or its alloys, the heat treatment is not generally done in very high temperature. It is generally done within this temperature range. So, for the application point of view, the study of ferrite and austenite is very important than that of delta iron. Now, we can see different microstructural constituents of iron carbon system. Now, we will meet each of them in the later parts of the diagrams, but before that, we must learn something about them, what they actually are. So, first of all, austenite. From the previous diagram of allotropic forms of iron, we can see that the austenite part or gamma iron is generally seen at temperatures from 910 degrees centigrade to 1404 degrees centigrade, and it is generally FCC in structure. Now, austenite is a solid interstitial solution of carbon in gamma iron. Now, from phase diagram, which I am going to show you later, you can see that the carbon solubility of carbon is highest in this case, and it attains around 2.14 degrees centigrade at around 1130 degrees centigrade. Now, it is ductile and has higher strength than ferrite. Now, next we are going to learn about ferrite. Just like austenite, as you have seen in the previous diagram, the ferrite is BCC in structure, and it is generally seen up to 910 degrees centigrade. Now, from the phase diagram, you can see that the solubility of carbon in ferrite is maximum at 723 degrees centigrade, and that maximum solubility is also of 0.025% only. Now, from both this part, it can be easily seen that in case of austenite, the solubility of carbon is much more higher than that of ferrite. Ferrite is soft, it's highly magnetic, and it does not harden when cooled rapidly. Now, let's come to cementite. Now, cementite is nothing but iron carbide. It contains around 6.69% of carbon and has a complex rhombic lattice, and under normal condition is extremely hard and brittle. Generally, when the carbon content increases, we will come to see the formation of cementite from the phase diagram. And in case of cast iron, the brittleness and hardness of the cast iron is generally controlled by the presence of cementite. Moving on, we will see pearlite. Pearlite is a mechanical mixture of ferrite and cementite. It is formed generally due to the transformation of austenite of eutectoid composition, and it forms different layers of alpha ferrite and cementite alternately. It contains around up to 0.8% of carbon, and it is soft and is up to 8% of carbon. The ferrite and pearlite is soft and is called hypoeutectoid steel. And when the percent of carbon increases from 8% to 2%, is called hypereutectoid steel, and it is a mixture of pearlite and cementite, and it is generally hard and brittle. We will see all of these parts in the iron carbon phase diagram that I am going to show you next. Now coming to benite, it is a ferrite cementite aggregate formed by isothermal decomposition of austenite. The microstructure attains alpha ferrite and a fine dispersion of cementite. Now you can see venite, martensite, trossite and sorbite. All of these things we are going to see in the time temperature transformation diagram, which will be shown to you in the next video. So I will be providing these notes in PDF form to you, so you can go through all of this. Now let's come to the phase diagram of iron carbon system. Now this is the phase diagram of the iron carbon system. So first of all, up to 910 degrees centigrade and below it we can see alpha or ferrite, and the solubility is around 0.025%, which is very low, and that maximum solubility is also at 723 degrees centigrade. Now at our higher temperature from 910 degrees centigrade to this line, which is 1404 degrees centigrade, we can see austenite, and above that we can see delta iron generally. Now this part is not generally that important because the heat transformations, heat treatments are generally not done at such high temperatures. So we definitely peritectic point is important at this part, but other than that we must see the other part, the rest part of the diagram. Now the liquidus line is here, given here. So the liquid is separated by the liquidus line, and this is the solidus line stated over here, and the solidus line and the liquidus line meet at a point which is called the eutectic point, and the eutectic temperature is 1130 degrees centigrade, and the eutectic composition is 4.3%. Here you can see 4.3% of carbon. Now we can see another point which is important. It's peritectic point. Now what sort of reaction takes place, I'll be discussing it later. First of all, see the diagram first. It does the peritectic temperature is 1404 degrees centigrade, and composition is around 0.018% of carbon in iron. Now you can see that for austenite the maximum solubility of carbon is at around 1.8% or 2% of iron of carbon, and that is attained at 1130 degree centigrade. Other than that, as we move towards the right, what we can see is that the carbon content increases, and with the increase of carbon content we can see the formation of cementate, and as the carbon content increases further we can see the formation of ladurite too. Now this point is called the eutectoid point. Now eutectoid temperature is 723 degrees centigrade and the composition is 0.8%. Now as I have discussed earlier, that within from 0 to 0.8% of carbon we call it hypoeutectoid steel. Hypoeutectoid steel, and this steel generally consists of ferrite and pearlite, but as the percentage of carbon increases from 0.8 to 2%, we call it hypereutectoid steel, and in that case we find pearlite and cementite. Now this steel is much more harder than hypoeutectoid steel. Up to 2% we consider it steel, but as the percentage of carbon increases up to say 6.7%, we call it cast iron. The temperatures are very important that you must understand. Okay, the eutectoid temperature is 723 degrees centigrade, eutectic temperature is 1130 degrees centigrade, and peritectic temperature is 1404 degrees centigrade. This is the melting point of iron, that is 1539 degrees centigrade, above which we get liquid form of iron. Now we will discuss about the reactions that takes place at these 3 points and what are these 3 points actually called. First of all, eutectic reaction. You know about what eutectic point is actually called. It is the point of intersection of liquidus and solidus. Now the for iron carbon system, the eutectic temperature is 1130 degrees centigrade and the eutectic composition is 4.3% of carbon. Now the reaction that takes place is liquid iron transforms into austenite, that is graphite and cementite. Now we go to the eutectoid reaction. Now when one solid converts into two different solids, it is called eutectoid reaction. In case of iron carbon diagram, we can see that austenite transforms into ferrite and cementite, which are two different forms of iron. So that point is called eutectoid point. Now the eutectoid temperature is around 723 degrees centigrade and the eutectoid composition is 0.8% of carbon. Now at this composition, carbon remains generally uniformly distributed over above 723 degrees centigrade. But when the temperature decreases below 723 degrees centigrade, it will be seen that the carbon diffuses from their interstitial sites and they form plate-like structures of alpha ferrite and this is carbide, iron carbide, and they form alternate layers which together is called pearlite. Now this pearlite is generally formed at eutectoid composition only. In the similar manner, eutectic composition will produce only ladybirite structure. Now the eutectoid reaction is austenite on cooling gives ferrite and cementite, or both together called pearlite. And lastly, we must go to peritectic reaction. Now when there is a huge difference between the melting materials, here in this case we are watching iron and carbon, and the temperature melting point difference of iron and carbon is very high, very huge difference. So in this type diagrams we will see peritectic reaction taking place. Now peritectic reaction, what happens, it does take place at 1493 degrees centigrade and at a composition of 0.18% carbon. Now what does happen over here is liquid iron and delta iron on cooling forms austenite. So this basically consists of the iron curve phase diagram. What you need to study from here will be given you in a PDF note. There are other parts of this chapter too, so I'll be coming back again with the rest part of the chapter in another video. So everyone, stay home and stay safe.